Hello everyone, as we have earlier discussed about the gradient descent, now let's discuss about the learning rate alpha. So here we know that W is equal to W minus learning rate of cost function, differential of cost function. Let us see how a learning function affects the gradient descent. Now if we see, if let's consider the first case where alpha is too small. So when let us consider in this graph we are at this position, right? Like presently at this position. So when alpha is too small, when we differentiate it, even though the slope is more, as alpha is very less, so as it is in some 0.00 some points, so even if you multiply the large value of the slope to the 0.000, the difference will be very less. So the steps taken towards reaching the low value of the cost function is too late. It's like it takes more time, right? Yeah, that's what I mean. Next, it takes more time to reach the local minimum. Now let's take the different case, like case 2, where alpha is too large. So let's take, now we are at this position, like exactly at this position. So this is the local minima. So to reach this local minima, so we have again differentiated the value and we have tried to inculcate in this. So now as the value of alpha is large, the value of W may not reach the local minima at all. Like now we are at this position. The next step, even though local minima is here, we may reach here. So as here, after we reach here, when we calculate the slope and we do this the calculations for this, we'll reach here, we may reach here. From here again, if we do calculations, we may reach here, then again here. So in this case, there is a possibility that we may not reach local minima at all. Now let us consider the third case where we are already at local minima. So if we are here, like it is a local minima, right? So if we here, so if we calculate the differential, it is the straight line parallel to x-axis, right? The differential of this will be 0. Like even though if we are at any position, like W is equal to 3, 4, 5, at any position 10, 12, 13. So W is equal to 13 minus differential of 0 into alpha, which ultimately leads to the same position. So if we are at 13, let's assume that we are at 13, W is equal to 13. So W is equal to 13 minus alpha into what is the differential? 0, right? So ultimately we will stay at the same position. So if we are at the local minima already, so we will not move the position, so we can't move. So this is how it is. Now let us consider the next case where we have fixed learning rate. So fixed learning rate, even though we have a fixed learning rate, we may face problems reaching our local minima. So now let us suppose we are at this position. So for reaching this position, we'll try to calculate the differential and we'll gradually descend towards this position. But as we descend, we'll face some problem. Like what is the problem exactly? So let us consider. So if we consider this point, the slope is relatively bigger, right? So it is better. So as we move to the next point here, the slope gradually is decreasing. So next, as we move to the next point, the slope even more it is decreasing. As we move closer to the local minima, the slope is decreasing very rapidly. So if we come here, the slope will decrease and the slope is very small that we'll need to take very tiny steps to reach the local minima. So even if we have the fixed learning rate, it takes more time to reach the local minima. So this is how we can wind up the gradient descent.